Okay, hello everyone. Welcome to another Wolfram Language Design Review. We are talking today about machine learning. And where are we starting? We're starting with feature extraction with no training, which is something we should have implemented a long time ago. So, no. We already talked about this. We're not doing this, right? This is the default behavior. That we need to make this, okay.
Okay. There's like we need to take. I mean, we need if you don't want to introduce yet another symbol, which I think is bad.
Well, we might have to deprecate what we have right now.
Okay. I mean, but I wanted to bring it to your attention before doing something more drastic.
Okay.
Yeah?
So what? Right now, feature extract returns what?
A feature extractor function. No, sorry, feature extract. No, feature extract returns the features. So feature extract is the same as feature extraction with the feature property as a return type.
But so it's using a default feature extractor. Is that correct?
Yes, it's going to a numerical vector, basically.
No.
Unless you specify something different.
I understand that, but it is not learning the feature extractor from the data. It is using a default feature extractor, correct?
It is. I mean, right now it is learning. That's a standing behavior. So this was always this way. If you do feature extract of stuff, it's basically is a shortcut for like training and applying. It has always been that case. Okay.
So when should we be training, and when should we just be applying?
So let's say the nice thing about the training thing is that you don't think about stuff. You have your training, it goes with the training test paradigm.
No, but it has to get primed somewhere. It has to know how to convert an image to bits and so on, right?
It does, but we have very powerful extractor like the
I'm aware,
numerical
so what
vector
are we going to do?
extractor.
Right, I understand, but what does it do?
It has pathed from every data type, basically. It starts from, it has several branches.
I understand that, but what do we do with, in the case where we are not training, aren't we just using that feature extractor?
In some, I mean, I have a detailed analysis of this. This depends on the extractor, because some of the extractors are actually pipelines, some are simpler. So in some cases, the extractor itself is not data dependent. Like, for example, if you want to extract features from an image, running a neural network does not depend. You don't run a different network based on the image. You always run the same network. So you should always get, regardless of how many images you have in your training set, for example, you should always get the same features. But the way is paired up with the rest in the pipeline, there are extra steps like image conformation, which is input dependent, because if I have only LAB images, then it becomes LAB space. And you have like a dimensionality reduction step, which is appended to many extractor to avoid inflating.
Okay, let's be clear. If I say feature extract on one image, what's it going to do? Okay, but it needs to work, right? It needs to work using the default feature extractor. Do you see what I'm saying?
I mean, it cannot unless we modify what the default feature extractor is.
I know. That's the point. I know. That's what I'm saying. Right? We never committed to leave the feature extractor. That's why we built a whole bunch of things for building, we never committed to leave the features that you get to be the same for all time.
No, that's true. That's correct. And this is why this is a possibility. And I actually have it up as a possibility.
Okay.
Yeah, in terms of
so I mean, to me, feature extract of a single image should use the default feature extractor and just give the whatever we can from that image.
Okay, right? Then
so similarly here, I don't think that there's a point in training from 5 images. Nothing useful is going to happen by training from 5 images, is it?
No, the only thing you do is you don't actually train the feature extractor from image to vector. What is trained is a dimensionality reduction step.
Okay.
Yeah, well, and I agree that there is a little point here, because I mean, that would make sense if that would be your whole training set, not just a sample. Yeah.
Yeah.
But in general, I think we've been a bit obscure about this specific point. It's not super clear, and it's probably better to be consistent and only have the same set of long vectors.
Look. I mean, there's a question of if you add one more dog, does that cat change?
Yes.
Right?
Potentially, yes.
Yes, I think that's reasonable by default. I think you should be able to set it so it doesn't change, but by default, I don't see a reason it shouldn't change. Am I making sense? So what I'm imagining here is that, feature extract, I don't know what's the difference between feature extraction and feature extract.
Feature extraction trains an extractor function that can be reapplied. Feature extract is basically the same call and then applies the extraction immediately.
Okay,
it doesn't return you
feature
the
extract
function.
should be the primary function we deal with, and it should work without training, like for a single image and so on.
Okay, I think the proposal that caters to this request and aligns with what we've been discussing so far is that we change what automatic means. When you don't put the second argument. If you say image features as a second argument, my proposal is to change what it does and don't add the dimensionality reduction automatically. And I don't think it's a big deal, because if you do want, we do support pipelines. Yeah, so you can have a list, image features, dimension reduced vectors. That would be the same as the old one. If you don't explicitly ask for the dimension reduced vectors, you will not do the dimensionality reduction.
What dimensionality do you get if you do dimensionality reduced vectors?
It depends on the number of examples. Yeah, because it depends on the variance. Ideally, if you have only one image in a list, it should be like a vector of 1, 0. Yeah, it's standardized.
Yeah.
So, which is why
I mean, in this case, there are 5 images, and it's a 4-dimensional, feature vector that's coming out. What determines that?
I have to look at the code internally, but it depends on how much variance you have in the feature vectors. So if you add a lot of cats that are close to these, it will not grow much. Yeah. If you start adding boats, it will probably grow faster because it has to accommodate.
The main point is that it is automatically determined what the dimensionality of the feature space is here.
Yes,
correct?
Exactly.
Okay,
correct.
So we can change what that means. I mean, we're just giving people a feature vector. We're not telling them it's going to be a particular dimensional feature vector.
No, and I think this is why in the automatic case, this result is fine. But if you put that comma image features, I think this is going a bit overboard because it's not reproducible.
No, I agree. So I think, okay. So let's be clear okay. So one thing is there are fixed feature extractors. Another thing is there's train the feature extractor, right? The fixed feature extractors do things like image feature vectors and dimensionality reduction. And those are things which are fixed known operations, correct? Reproducible every time.
Yes, for the first one, not for the second one. Dimensionality reduction is trained, standardized. That stuff depends
on the data. It's data dependent.
Exactly, it's data dependent.
Right. Okay, so some are data dependent, some are not.
Exactly. Okay. So my proposal is to make it explicit in the pipeline. Yeah. So instead of having that image features has an internal step of dimensionality reduction, we remove it and we add it external. We add it to the default pipeline.
I got the idea.
Okay.
Right. So okay. So here, the only change really would be feature extract could take a single example, for instance.
Yes.
And give a feature vector in a reproducible way, or at least reproducible within a given version.
Yeah, I mean, no, yeah, exactly. Because the rule we always had is that if you export the extractor, is always guaranteed to return the same result even in future versions.
Well, I understand, but that's the feature extractor function. Feature extractor itself is, I mean, I think we should support a method option, okay? That we should support starting now, that has a version number, right? So if you want to get the feature extractor from version 14.3, you'll always be able to do that. Do you see what I'm saying?
Yes. Okay. We could have a mapping from language feature, language version to feature extractor version. So even if you don't update, you can always specify a language version that will be resolved.
Right.
Yes.
But I mean,
yes.
My point is this, that we've done that for some other functions. Like I think we did that for random integer. I think we do quotes version blah blah blah. Okay.
Okay, I'll go looking in random integer.
I think that's the right one. I think that's the right pattern. But that's what we should do starting now. Is and you know, if we are changing it from what it was in version, we should do it, version whatever it was, 11 or whenever this was introduced, right? We should say that's 11. What do you know? I was right. It's been a while.
Yeah.
No, so we would say,
I was proposing to support every version. Like you could put 13.2, and that would it doesn't matter if it's the same or 13.1.
Yeah, look at what's done in the other functions. I'm not sure.
Okay.
But yes, that's a reasonable thing to do. Except, I mean, okay. So, then this would return. Go ahead. What?
But I mean, what you propose is effectively applying what you have in the other notebook. Yeah. Like is basically defining an extractor function that takes no data. So it's still going to be a building block of this change.
Okay, hold on.
Yes.
The main function that we would promote is feature extract, right? Feature extract gives you a feature vector from data, right?
Yes, correct.
It is a single feature. So if I say feature extract / at a bunch of images, that will give me a non-data dependent, the definition of the feature extractor function will not be dependent on the data, be a fixed feature extractor. Am I making sense?
Yes.
And I think the rest of this, I mean, the only ambiguous syntax is a single list of numbers or something. In other words, what is for a single object? I think
a single list of numbers is a list of example with scalar values. But this is not, I mean, this is already ambiguous now. Yeah, it doesn't change.
No, I understand. So a single image or a single audio or something like that, we know what it is. Otherwise,
you can disambiguate, yeah, because we have a feature types. So if you say feature types numerical vector, that's going to be a single example. If you say feature types number, that's going to be a list of examples.
Okay, fine. Then we already have that solved.
Yeah.
Because
this was an old problem.
Fine. Yeah.
Okay.
The rest of it, so far as I can tell, looks just 100% fine. Okay, so that's feature extract. Now, feature extraction, the main reason to use it is to get a feature extractor function that you can use multiple times. But the only reason to do that is if it is data dependent, if the extractor is data dependent.
Or it could be that is like you decide on a pipeline and then you kind of save it by baking it into a feature extractor function.
Well, but look, the point is that the individual, feature extract is just, I just want my audio features, and I want, for example, for the extractor, I want my what is it called? MFCC features, right?
Yes.
I just want to, I say feature extract a piece of audio, MFCC, kaboom, I've got the MFCC features for that piece of audio, right?
Correct.
And when it's a single audio thing, obviously don't give a list as output. It's list in, list out, non-list, non-list.
Yes. No, this is already, yeah, of course. This is like what we do in classify, predict, and all the other functions. Yes.
Fine. So here, this becomes a much more minority function. I mean, it becomes the function that, as you say, bakes in a feature extractor based on that is learnt from data.
Yeah, I mean, I kind of see your point here. Like you could say that feature extraction non, extractor is actually, when you apply it, is like saying function of feature extract hash comma extractor on a single example. So you can like kind of, in terms of like, once you apply it, they kind of are blurred into each other.
Right. I mean, this thing here is a way of making a feature extractor function that does the same as what feature extract does without with a specific non-data dependent extractor, right? So it's a minority. Yes. I mean, that's a minority corner. So, okay, I retract my objection to this. I just don't think it's the thing that we front and center document.
No, and I understand your point. I think it's a good point, actually. I think I was a bit too focused on the extraction just because it's the main function that does the job. But extract is easier to understand for users,
right?
Because it's feature in, feature vector out.
Yeah, right. So, okay, that seems reasonable to me. Does Roger have any comment on this?
I agree with you. I think that sounds good.
Okay. All right.
Okay, there are like few technical things about this. Like this, of course, if you don't have data, this should inherit the type of data that is required by the extractor you specify. So if you say feature extraction, lowercase text, the input is text. If you say video features, the input is video.
I'm sorry, I missed what the point was here. What are we saying here? The type is inferred from the extractor input.
Yeah, I mean, you don't have training data, yeah? So in principle, if we have, if you have a list of features for each example, and the video is the second element, you can still use video features and it will be applied to the second element. If you don't have the input, we assume that you want to work on like naked features, yeah? Like if you say video features, we assume that you want to apply this on videos. And I think this is a fair assumption and matches what we want to do in the...
Okay, hold on. You're saying if I make a feature extractor function that just takes in video and I feed into it a mixed mode piece of data, is that the case you're talking about?
Yes, because in general, if you are training, one advantage we have is that if you're training on a tabula and you have, like a numeric column, an image column, and a video column, and you say that you want video features, then you can apply the feature extractor function on the tabula and only process that column.
Right. I think that's perfectly reasonable. That's the perfectly reasonable automatic behavior.
Okay.
But we also have this mechanism in here, the spec mechanism, right, which we could use here as well. I don't know
exactly. Yeah. See the second line after that. Yeah. One video feature, two lowercase text. This then assumes a list of video and text. Right. And you can make it even more general with like movie video features title lowercase text. In this case, it will work on an association or tabula or dataset with the movie and title column.
I like it. But this is already supported, basically. The case that you're addressing is this case where you have a feature extractor that expects a certain type, and you say you're going to, by default, pick out those columns that have that type.
No, I'm saying that is not possible to do in this case because we don't know which column has the type. Yeah, in the extractor.
In which case?
Like in the case where you have only a single extractor, we must assume that you're only passing a list of videos or a list of molecules.
Fine.
Because we don't have information about the structure of the data set. We cannot allow that level of freedom in the framework. It's really too much. We are already quite free for all as we are.
Okay. But I think this is pretty reasonable, and I think particularly with this association support, which I assume, I don't know whether that was there already, but feature extract on a tabula, right, which obviously you have to support here, right?
Yeah.
Feature support of a tabula with, I mean, that's pretty cool, actually, honestly. Feature support, I mean, okay, so may I make a comment here? I mean, okay, this, we've got extractor names. So I think we should be able to say movie arrow automatic, title arrow automatic, and it should look at the type of that column of the tabula to decide which feature extractor to use. Does that make sense?
Even without training data, or only if you have a tabula?
Only if you have a tabula.
Okay, that makes sense then. Yes.
Okay. What is this?
Okay, so this is a bit like, it's not only about dimensionality reduction, but dimensionality reduction is the kind of the main culprit. one of the reasons why many extractors are not usable without training data is because they have a dimensionality reduction step. So
yeah.
One way
you're
that
suggesting factoring that, or alternatively, I don't quite understand why we're not just saying, we get out a bunch of feature vectors and then we say dimension reduce on those feature vectors.
Yes, I mean, we even have a reduced dimension extractor that you can pipe. So you can effectively, go back to the same behavior by piping
if you want to, but I mean, the other thing you can do is just say dimension reduce, right, on that list of vectors. Am I wrong?
Yes. Yeah. No, you can. Of course you can. You can pipe the function as well.
Yeah, I mean, that looks beautiful. Why did we put dimension reduction into the feature extractor by default in the first place?
I think the idea, I mean, this was like way before my time, but I think the idea was that you don't want to, provide too many features. I mean, I think that, okay, going back to the beginning, I think the main idea is that this whole machinery was set up for classify and predict. And you don't want to swamp, logistic regression with 1,000 features when you only have, if you do a rotation, you only have 10 significant dimensions.
Yes.
Yeah, so I think this is the main problem here. But this makes perfect sense when the whole pre-processing happens inside classify. It makes less sense when you lift it out as a separate function.
Yeah, I mean, look, I think the notion of embedding spaces and feature spaces and so on has become better understood in the decades since we first implemented this.
Most likely, yes.
So, I mean, I think, so your proposal is, as you were saying before, don't do the dimensionality reduction by default in feature extract.
Yeah. I mean, we could also have that we do it if you train and we don't do it if you don't train. But I mean, I like your idea that is you do it if you don't specify the extractor, so you are fully automatic. And if you do give a name, you don't do it. This seems legit to me.
Sorry, if you're doing fully automatic with a list of data, we can do it.
Exactly. So if you do feature extract of a list of images, you automatically dimension reduce. Yeah. But if you do say feature extract list of images, comma image features, you don't do it. And same thing here. So you don't automatically add it to the pipeline if the pipeline is explicit. But if it is implicit, you can.
I think that's fine.
Okay, then we can skip to the rest. I mean, if you want to open this extractor situation, that's going to tell you, how many can work directly. The first column is what we document. The second column is the internal pipeline, which could be one or more extractors. The third column is the extractor itself data independent? And the final column is, can we allow to use it with no training? And you notice that you have some extractors that are not data independent, but we can use it with no training. And the reason is that you can set defaults.
Yeah. Well, missing
so
imputed, I mean.
Yeah, exactly. That is false and forbidden. So that is hopeless. Exactly. But some of them, even standardized, you could say that, that you have mean 0 and standard deviation 1.
Sure.
Whatever. Yeah, some
Why
of them.
Is numeric vector are not possible to do with data free?
Because numeric vector is a super powerful extractor that no matter what you put in, gives you a number. So that's extremely data dependent. That is like the hammer, basically.
I don't understand, but why isn't there a default for
that? Because some stuff might be like for example, you might have sequence statistics or other things. I need to check into the details, but it's a very large pipeline, and you just need one internal extractor to be dependent on the training to break it. But some are some we can easily get around, like the audio spectrogram one. We can have defaults. But you see that, for example, we have at the bottom of this list, we have graph features. And you see that internally, this is a pipeline that has this graph extract features, which is data independent, and a dimensionality reduction step, which is not. So, if we remove that, we can make this data independent.
Sorry, I lost concentration for a second. Could you repeat that?
Okay, so if you look at the bottom of this table in your screen without scrolling, you have the graph features. Yeah? So graph features is an example of what I was saying before. It's a two-step pipeline internally, extracting the graph features and reducing the dimensions. Yeah. So in this case, we can make it work by simply skipping the dimensionality reduction part.
I'm sorry, I'm still confused about the numeric vectors. If you feed it, a random pile of crud, okay? Isn't there a default way to get a vector of numbers out of that? And why aren't we just giving that? Why does that have to be?
Because it's, for example, I was thinking about this like on a separate thread, and I think that, for example, nominal to numerical depends on how many nominal classes you have.
Well, but it doesn't have to. I mean, think of that numeric vector as being like a hash, basically.
Okay, I mean, I guess we can look at the pipeline and make sure that there's no step that can
make a default. I mean, look, the fact is, think of it like a hash.
Mm-hmm.
It's a a kind of a hash where it tries to make nearby things have nearby hashes. See what I'm saying?
Yeah, I mean, I understand your point. I don't want to overcommit. Let me check the code. But I mean, I can promise that we'll look at that, and if it is possible, we'll definitely make it. Then some other things that we can be a bit more like arrogant in setting defaults is, for example, conform data. We could say, for example, that we have a default image size, and default color space and stuff like that. So that I was like leaving it for like kind of round 2, but so we did one pass and clean up most of the stuff. But I think now this is good because we have a full picture and we can like aggressively go on and make, I would say, almost all of them allowed with no training.
Okay.
So then I was trying to use some examples of what you can do here. This is, toolbox. This is fine. This is a new extractor, like sentence vector.
Cool.
This is new in 14.3, and it was fairly well. Like it's a small model, but is a lot better than what you had before, and it will work fine on a CPU. So this was good. My goal. And now, here I was looking at some example. Like if you force non-feature extractor, basically one advantage that you have by skipping dimensionality reduction step is that feature space plot will work on the unreduced data, which might be better because like stuff like TSNE and UMAP, they are happy to deal with high dimensional vectors. Yeah, so you don't need that in the pipeline. And so I mean, wait a second.
Yeah. Here the issue is what? That if you give the feature extractor, if you don't give the feature extractor, what happens?
I mean, here is like to test like 4 different extractors. Yeah, the first one, molecule features, it has a dimensionality reduction step. So if you force it not to have it by saying feature extraction none, then the method will see the uncompressed vector basically, not reduced beforehand.
Yeah, I think that most of the time you don't really want the feature extraction doesn't do dimensionality reduction most of the time. It's a different operation.
Exactly. I agree.
Okay.
So I think this is fine. We covered all of it, I think.
Good.
Okay, now we have statistics.
Mm-hmm.
So we have several things here. We have 2 new functions for like this is called non-parametric modeling. That means you don't want to specify anything about your function, and you want like a reasonable line that goes through the model. So there are 2 ways we prototype to do this.
Hold on. When you get the reasonable line, do we know a formula for the line, or is the line?
It depends.
In one case.
Exactly. So like the two offers that we have here are like local model fit is doing local polynomial regression. That means that for every point you try to fit a line or something higher degree, but typically a line. Exactly. Yeah. I mean, in general, a polynomial. Then the other one is called local support fit. And what this is doing is saying, let's model your data as a combination of like a basis, basically, like automatic basis search. And you can model like a bunch of Gaussians, a bunch of Cauchy kernels. If you have outliers, for example.
What are the kinds of methods that are allowed?
You can open the ref page. You can specify your own function, but by default we try to be not swamp the user. So we put Gaussian, Cauchy, linear, and constant.
I hate the name. I like the functionality. I hate the name.
Okay, I mean, these are like temporary names. I'm happy to talk about it.
So what's the difference in this and find formula?
They're not closely related.
Why not?
Because find formula was just trying to find a global formula for something. This is
finding local ones.
Yeah, many local ones. And it's a little bit more like interpolation in the sense that our interpolation uses piecewise polynomial interpolation. So it uses many simple ones, basically.
Right. So it could be using, instead of piecewise linear, it could be using piecewise Gaussians or something.
Right. It isn't quite like that. I mean, the way this is also known as a kernel method, right? Because you still do linear combination and they overlap. So they're not piecewise in that, they overlap.
I see.
Okay. Yeah, you see in that plot, in that plot they do overlap.
And what's the relationship between this and various kernel estimator functions that we have?
Well, I mean, it's sort of often the same kernel group of kernels. You vary them a little bit to the problem. So we have this smooth histogram distribution and kernel mixture distribution and so on. And they use various forms of PDFs, and many of these are actually also PDFs, if you can look at them.
I think the main difference is that here the data is a function, xy or xy, x1, x2, x3, y.
Rather than distribution of probability.
Exactly. You're not in distribution space. Yes.
Okay, but to me, something about fitting with kernels seems not a ridiculous thing for the name of this function. In other words, if I'm saying
kernel model fit would be a better name, probably.
Okay. So I mean, if I'm well, let's think about that for a second, okay? I mean, I'm thinking, okay, I'm going to model this with a bunch of Gaussians. That's the thing I might reasonably think, right? And then,
I mean, but the point of sort of you can do that yourself right now, like linear model fit. But the point here is that it adaptively, picks how many and so on. It's like in both of these, what you decide is how much you want to smooth and how detailed you want to track things.
Sure. But it's going to pick, is it 3 Gaussians or 75 Gaussians?
Yeah. And it's going to decide how many.
Right. That's nice. And presumably you can get out the thing that, you can. It's in this fitted model construct.
Yeah, exactly. Yes. I package that in fitted model. That's a formula. I mean, the reason to package it in fitted model is because this is technically a linear fit. So there's no reason not to give you extra information that you have in fitted model.
Okay. All right. Okay. So let's come back here. And by the way, does this work in any number of dimensions?
Yes, both.
Okay. So when this says local model fit, what are the local functions that it is fitting?
Polynomials. You have a fit degree option that, I mean, typically you keep it as 1, but you can use 2 or 3.
So what's the difference between this and this, except that here, I mean, I don't understand that there's things like a Gaussian, which has, a couple of parameters.
Okay, so in the one you have here, kernel model, you decide, I want to fit this thing with, I don't know, 5 equally spaced Gaussian. And the fit procedure is you're going to find the coefficients.
Where do you say 5 equally spaced Gaussians? How do you say
in this case, it's automatic. You can say that. You can say that bandwidth parameter can be a distance, or you can say a distance, and I should update this a bit. I was working on some automation to find that, and I need to update the automation table.
So how does this relate to the peak fitting function we have, for example?
This doesn't, because it doesn't try to give you. It is not built with the idea of finding one Gaussian to put exactly on that peak. Yeah. So this is more like, I want something that describes the function well, not something that models the peak.
Okay, but let's look at what is the one for peaks?
Peak detect.
Oh, peak detect.
Yeah, one returns a map and one returns the coordinates. They are like siblings.
Yeah, this is a nice and useful function.
Yeah, but this is a completely different thing. This looks at the signal.
By the way, they should have C alsos, obviously.
Yeah.
But okay, this is just, I only care about the peaks. This is what I want to get the whole function fitted.
Yes.
Right?
Yes. Yeah.
Okay. So I don't understand the difference between the local polynomial fit. Why is that different from, this is a local Gaussian or local whatever it is.
No, it's not local.
They're not local.
Is a sum of local functions, but the sum is a single expression. Yeah. So the end result of this fit is a sum of fits.
So this one is a piecewise polynomial fit.
This one is not even, we return an interpolating function, but this is a procedure. Like, you could evaluate this in real time. So the moment you plot it, you could say, what's the value of this function here? And the way to answer is to perform a local fit, a locally weighted fit.
I'm not understanding.
So this is not
okay. Interpolation.
No. So Stephen,
yeah.
So we since it's potentially very expensive to run another fitting procedure at every point you want to evaluate the function.
Yes.
One way is that you do it in batch, one go, and you package it up as an interpolating function.
Yes.
But that's like another approximation on top of your approximation. Do you know what I'm saying? It's not bad, but that's a way to get something you can evaluate very fast.
But local model fit in your setup has a value that you want to evaluate the fit at or not?
Can you open the page for local model fit?
Yeah, open it.
Yeah. So the first image is showing you, ideally, what happens. Yeah, like you wanna compute at one point, you look at the points around it with the bandwidth, and you perform a fit, and then the value of the fit at that point is the value of your model. So this is completely model free. Yeah, it doesn't have anything. It has a procedure to compute what should be there.
Okay, but then can you ask it? But it's still going to always return a whole function interpolating function. It's not just going to give you the value at that point.
No.
You mean you can?
If you evaluate it at that point, you will get the value at that point. But you get the whole function.
But wait a minute. Is there no reason to have a function that will, or have a way to just compute this thing at that point without computing it at all the other values?
I do have a way. So if you scroll down to the options, the way I package it right now is that you have interpolation points, which is automatic, and you can no wait. This is a way to package it. We can discuss it. Yeah. The last value of a table interpolation points is none. That is fully supported, but that requires, that's a discussion point.
So what the hell do you get out from that? What do you get out if you say none for the interpolation point?
You get something that saves the data and it runs the fitting every time you ask for it.
I can pre-compute a bunch of things, like I can pre-compute the nearest function.
Interpolation works. Does interpolation have a second argument that has the value, which I would never use? But
interpolation saves all the values, and it computes.
Yeah, find interpolation. No, look. This is the thing I'm talking about. This usage, find interpolation of data at the point X.
Yeah.
Yes.
Which we don't have in this case, although we could.
I don't think we should. I mean, in the fitting functions, we don't do that. I mean, it's kind of stupid.
Yeah, I agree. I've never used it for interpolation.
Right. So we should not have it. We really should.
I mean, it's relevant to the old-fashioned. My God, interpolation is so old.
Right.
Mm-hmm. Yes. I mean, honestly, Stephen, I had it in the first iteration of this function, and then we remove it because the design was getting more complicated.
I don't think it's necessary. I mean, that interpolation with that second argument is more relevant back in the day when you would regularly interpolate, printed tables of data and things.
Mm-hmm.
It's not
right.
It's not really a thing today because it's sufficiently cheap. Interpolation is a cheap enough operation. You might as well just do it to the whole function over the whole domain.
Yeah.
Okay.
So basically, the possibility here is that given that this is I think like most people will be happy with the interpolating function. If you really, really care about computing the fit point by point at runtime, you can force it not to interpolate. But in that case, I didn't fully document it because in that case we need a new object because that's not a fitted model.
Let's not go there. Okay, let's not go there. Let's just say we're going to do a one gulp thing where you just get the whole function out.
Yeah.
Now, the only case where I can imagine that goes wrong is in high dimensional data. I don't know how this applies in 10
so data. I mean, if you talk about we're going to need different solutions for super high dimensional data, like radial basis functions and other things. Interpolating function, if you do interpolating function in 10 dimensions or something like that, you're probably fucked. It has sort of a cursive dimensionality problem.
Yeah, I understand. But for high dimensional data, it would be nice if the automatic behavior just segued to compute on demand.
Yeah, it's possible.
And fitted model probably should have that possibility, that it segues to compute on demand. I mean, fitted model does.
I don't think it needs it, actually.
No, fitted model has a formula. Yeah. The only thing it needs, but this now is it. I updated the summary box 2 versions ago, so now is not at least it's not serializing the large data sets in the notebook.
So even interpolating function could be compute on demand in high dimensional data. There's actually, no commitment that it isn't.
No. Interpolating function is compute on demand. I think that the way when you evaluate it, it goes in and figures out where is my point, in which bracket, and then it figures out what nearby points it needs, and it runs like a Newton.
Does it? No, I thought that was already done inside the interpolating function.
But how can it be done for every possible point? It's done for like some points.
No, it's doing it when you call it.
Okay. So then it could be set up to have slightly different algorithms for very high dimensional data.
I think we need to look at other ways because just to think about sort of the tensor product, it's like an outer product of stuff. It grows very, very, very quickly.
Yeah.
So we need something sparse, and I think that what most people do, and I mean there might be others, but things like radial basis functions that are sort of set up for that.
All right. Hey, we're going to run out of time here in a few minutes. We're going to have to continue this.
Yeah.
But let me just see what else we have coming up here. This is something completely different, right?
Yeah. We could even move this to the LLM review.
Okay. Okay. So let's just have a quick look here. All right. I hate the name local model fit. I would never understand what the heck that meant.
Well, it uses a local set of points to do it. So, and that tells you how fine-grained it's going to be. If you're more local, it's more wiggly. If it's more global, it's less wiggly.
Okay, but that's kind of like a moving average.
Yeah, a little bit.
So, and by the way, that should be another C also for this.
Right.
But the moving average moving average is for discrete data.
Yes.
And it just gives you new data points.
Right.
But it's actually very close to moving average in terms of like idea.
Yeah.
Yes.
It's the same. It's sort of a type of low pass filter in a way, but it creates this infinite dimensional, a curve, a model, or a surface.
And it returns an interpolating function. Is that correct?
Yeah.
Yeah. Because we pre-compute the fit at I don't know, like
explain to me again, why is it different from interpolation itself?
Interpolation, things have to go through the point. That's what interpolate means. It goes through the points.
I see what you're saying.
Okay. And so this is an approximating function, and I think it will be as successful, I think, roughly speaking, as interpolation, which we use for all kinds of things. And it's really handy.
Well, maybe we could call it local approximation.
Well, I think that, but we have all the, I mean, we could have that too, but it has all the trimmings of a fitting function, which is all sort of, the quality of the model and all that, like error bands, which is very important. But we could do a local approximation version of the same thing, which is more bare bones, like interpolation is much more bare bones.
Well, what is the analog for interpolation of the quality of the fit type thing? There isn't one because it's just going through the data points.
Yeah.
Yeah, exactly.
It depends on your assumptions on where the data came from, of what I'm saying. Did you assume that your data was twice differentiable, how many times differentiable to begin with, and then you can make conclusions.
So you think this is going to be an important function?
I do.
So maybe we should call it local approximation.
Well, I think that the local approximation should be the bare bones thing that doesn't give you quality stuff.
But this doesn't by default. This gives you an interpolating function.
No, it gives you no.
Look at
this. Yeah. We decided that we don't return the runtime fitting function by default.
No, that's not what I said. But how do we get the error bands? I mean, that was.
I put it under a compute uncertainty true option.
What?
I mean, we cannot use fitted model for this, because it's not a model.
Well, we can't.
It's not a model because it doesn't have any underlying symbolic representation.
It does. Interpolating function is perfectly fine.
No, I don't necessarily. I don't understand what your expected return type is, Roger. Sorry.
No, Roger is saying this should return a fitted model, which is not convincing to me. I mean, in other words, fitted model has the same sub-value behavior as interpolating function. Is that true or not true? I don't think it does.
Yeah, it does.
No,
it does.
Does it?
Yes.
Oh yeah, it does. It does. Yeah. I mean, sub-value as you can evaluate it on something and get a number and get the result out. Yes.
Okay. That's weird. How do I get the data? I do information of this. Is that right?
You see this, unfortunately, it's still a sub-value.
Okay, so that's a hack, and we got to take that out.
That has been like that since forever.
I know. It's a bad idea, right? It's a hack. We got to stop doing it. Okay?
We can de-document it, but keep in mind that nonlinear model fit is one of our most used functions in statistics.
Yeah, okay, well.
I mean, let's do it carefully.
It's not the right design. Then we got the wrong design.
For what?
For what?
Then, look.
Information is almost impossible to know what's available in information.
No, I understand. The hack, which I never liked, I said it was a bad idea from the beginning, of having something where you feed in a number and it gives you a number, you feed in a string and it gives you some totally different thing.
I understand.
Is a bad idea. So
Yeah,
let's
but
not double down on that design because that design is bad.
I mean, I'm not doubling down here. This is exactly the same object. It's doing the same thing.
I consider that doubling down. As soon as we introduce a new function that compounds the mistake, we're doubling down. So let's take a look. I mean, the whole nonlinear model fit thing, we are updating, right? And it will not be a function with that name. Nonlinear model fit can go on doing exactly what it's doing right now. Okay, but it will not be the...
If you want to go there, we absolutely need another meeting.
Yeah, obviously we need another meeting. We need another meeting, right?
Yeah, no, we need it anyway, but...
Yes, but that's what I think we should be going towards. We should be going towards something which has a cleaner design.
But I think sort of the fitted business, I think one of the promises that we... and this shouldn't return interpolating function. In that case, it should be named something else. And we can have a bare bones that does kind of like fit does, or interpolation does.
Yes.
You know, it's a very bare bones. It tells you nothing about the quality or anything like that. Nothing else you'll find out.
We should talk about this. Okay. We might need a thing that is like, look, we're going to need something that is in between fitted model and interpolating function.
Let's talk about that next meeting then. I mean, we'll
but
come up with
I like the idea of going for a naming. You know, to me, local approximation is something that I can understand.
Mm-hmm. Well, I mean, okay. We were going for model fit because it should be in the model fit family. You know,
I know, but
we need a version like that.
Family is going to get blown up because I think that we know that the design of nonlinear model fit, for example, is kind of cruddy. Right. So let's clean this all up and use a different name and get all those things under a newly named, family, and then, move towards that design.
Okay.
That's what I think. But I think I need more time with Roger to hammer it out because this is not a small thing. No, I mean, we are already discussing about it, and we are fully aware. But it's a big move.
Yes, but anyways, I mean, regardless of the packaging there, which we can come up with it, and it's important too. I think that this function and the other one, the sort of model free, is incredibly practical.
No, I like them very much. They're great, and I also like the ability to put them into visualizations easily.
Yeah,
it's great.
Yeah,
it's great stuff.
It's gonna be even easier once all the updates in these are merged. Like it's, I'm working together with that team, and this is going hand in hand.
Okay, I think this is great, and I mean, while we're at it, let's get a target for the redesign of nonlinear model fit. Okay,
that's for the next release.
No, I know it's not for this release. I want a target, right?
What do you mean by that?
I mean, I want to know roughly what direction we're going so that we make all these functions nice and consistent.
Oh, I see.
These functions become consistent with the future.
I think that we can do that. Let's finish this version.
I want to make sure that we're not going to get an incompatibility with where we're going with those other functions. So we don't need to have nailed it down, but we need some rough direction. Because the issue we have is we've got two different things we're trying to do. We're trying to get values out and we're trying to get metadata out. Right?
Yes.
Okay, so we got to address that issue. I don't know exactly how we address the issue.
It's not going to be quick, Stephen. We're working our way through that.
No,
and that's what I'm saying.
That.
So
I realize that. We need an idea for how to do that.
We have several ideas.
Okay, good.
We're going to spend weeks on that, Stephen, now. But if you want to spend weeks on it now, we can.
Let's try doing one more meeting. Okay.
Okay.
Right. Let's get one more meeting about that, and let's see how far we can get. Bring the various suggestions. I hope
we don't have all the research done either.
Okay. Well.
Okay.
Then we'll get whatever we can get, and we'll have to base it on. But we're not going to go and build a bunch of functions here that have a definite design that double down on a mistaken design that we had before. Right. I mean, let's get these functions to be functions that hopefully are, if we say, well, there's this and this possibility for how we design these other things, hopefully this will be neutral with respect to those design decisions.
It depends on those on the direction.
Let's try and let's try and figure out the direction. Let's not make functions here unless we give them ridiculous names that we're going to be able to throw away later. Let's not build functions here that double down on the wrong design.
Well, the one above is actually called typically locally estimated scatter plot smoothing.
Yeah, low S.
If we spell it out that way, is a perfectly throwaway name.
Let's call it low S.
Deeply.
It's very Fortran-esque.
Yes.
And very nice.
Yeah. Okay, great.
Oh wait, but you could also call it Savitsky Golai filter, depending on the field you're coming from.
17 million other things. Okay. All right. Well, it's nice functionality. All right. Get another meeting.
Okay.
Let's try and continue this.
Okay.